Welcome to the lecture series on electromagnetic field theory. This is lecture number 1, Maxwell's equation. In this lecture, we are going to see different forms of Maxwell's equation, such as differential form, integral form, mixed form, circuit form, Maxwell's equation in complex field quantities, Maxwell's equation in terms of instantaneous field quantities, etc. So, as we all know that there are 4 different types of Maxwell's equation, which are based on 4 different laws. The first law is Faraday's law. The second one is Ampere's law. The third law is Gauss's law for electrostatics. And the fourth law is Gauss's law for magnetostatics. So we are going to see all these 4 Maxwell's equations in different forms. So basically in this lecture, I am going to cover these many topics. First is instantaneous field quantities. Second is Maxwell's equation in differential form. Third is Maxwell's equation in integral form, where we are going to use Stokes theorem and divergence theorem. Next, we are going to see relationship between circuit quantities and field quantities. Then Maxwell's equation in mixed form, that is using both circuit quantities and field quantities in Maxwell's equation. That is why we are calling it as mixed form. Next will be Maxwell's equation in circuit form. Then we will see complex field quantities, and then finally we will see Maxwell's equation in Phasor form, or you can say Maxwell's equation in terms of complex field quantities, which we also call it as Phasor form. So before starting, I would like to show you all these forms. This is Maxwell's equation in differential form. So this is the first equation, second, third and fourth. So these 4 equations constitute Maxwell's equation in differential form. Why differential form? Because here the differential operator del is used. There is one small thing which you should notice, that the time derivative is also a partial derivative. When the Maxwell's equation is written in differential form, the partial derivative with respect to time is used. Whereas in case of integral form, the partial derivative has changed to the normal ordinary derivative, that is d by dt. And the del operator has been exchanged with the integral operator. That is why we call it as integral form. Next is Maxwell's equation in mixed form, where we have field quantities E, H, B and D, and we also have circuit quantities such as psi, which is magnetic flux, and psi E, which is electric flux, I, which is current, Q, which is charge. Next we have Maxwell's equation in circuit form, purely circuit form, where V is voltage, U is electromotive force, Q is charge, I is current, phi E is electric flux, and psi is magnetic flux. So psi E is electric flux and psi is magnetic flux. So the superscript E has been used for representing electric flux. Now finally Maxwell's equation in Phasor form, where we substitute this differential operator, the time derivative with j omega, and the scripted fields which represents instantaneous field quantities, that is E, H, B and D, they have been replaced with the Roman letter E, H, B and D. Okay, so let's start. So instantaneous field quantities. So here we are going to use scripted letters to represent instantaneous field quantities such as electric field, magnetic field, etc. So electric field E in a scripted letter will represent instantaneous field quantity. So E represents volts, electric field intensity, its unit is volts per meter. H is magnetic field intensity, its unit is ampere per meter. D is electric flux density, its unit is coulomb per meter square. B is magnetic flux density, its unit is Weber per meter square. J is electric current density, its unit is ampere per meter square. QV is electric charge density and its unit is coulomb per meter cube. So the important thing which you should notice is that the field quantities are written in scripted form, that is E, H, D, B, J, etc. QV. These are written in scripted letters. These letters represent instantaneous field quantities. Instantaneous field quantities. Okay. Later we will see that how the Maxwell's equation can also be written in terms of complex field quantities or Phasor quantities. So first we will see Maxwell's equation in differential form. So this particular equation is also known as Faraday's law or Maxwell-Faraday law, which tells us that the curl of electric field is negative time derivative of the magnetic flux density B. Okay, this particular equation is also known as Ampere's law or Ampere's circuit law. It tells us that the curl of magnetic field H is equals to time derivative of electric flux density D plus the conduction current density J. This particular equation is also known as Gauss law for magnetostatic field. It tells us that divergence of magnetic flux density B is equals to 0. That means the total magnetic flux passing through a closed surface is 0. It also represents that an isolated magnetic charge cannot exist. That means a magnetic charge should always exist in a dipole fashion. This particular equation is also known as Gauss law for electrostatic field, and it says that the divergence of electric flux density D is equals to the electric charge density QV. Okay, and this particular equation is called the equation of continuity, and it represents conservation of charge. and it is written as the divergence of electric current density J is equals to negative time derivative of the electric charge density QV. Okay, so this Maxwell's equation has been written in differential form. Why? Because we have used the differential operator del and we have used the partial derivative delta t delta by delta t. So that is why they are known as differential form. Okay. Next we will see Maxwell's equation in integral form. In order to find out how these integral forms are written, we should also know something called as Stokes theorem and divergence theorem, because the Maxwell's equation in differential form can be used to find out the Maxwell's equation in integral form using Stokes theorem and divergence theorem. So let me show you how. So let me take the first Maxwell's equation, which is del cross E is equals to negative delta B by delta T. So if I do surface integration on both sides, so del cross E dot ds is equals to negative d by dt surface integration of b dot ds. So according to Stokes theorem, it says that a surface integration of a curl of a vector can be represented as the line integration of that vector. So the left hand side of this equation can be written as line integration of E dot dl is equals to negative d by dt surface integration of b dot ds. This is what is written here. Okay. Similarly, if you take the second Maxwell's equation, that is del dot B equals to 0, and you do volume integration on both sides, that is volume integration of del dot B dot d tau is equals to 0, and you apply divergence theorem on left hand side, you will see that this triple volume integration of divergence of vector B can be written as the closed surface integration of that vector. So it will become closed surface integration of B dot ds equals to 0. This is written here. Similarly, the third equation is curl of magnetic field H is equals to time derivative of d plus j. If you apply surface integration on both sides, you will see del cross H dot ds is equals to d by dt surface integration d dot ds plus surface integration j dot ds. So if you apply Stokes theorem on the left hand side, it can be replaced with line integration of h dot dl is equals to d by dt surface integration of d dot ds plus surface integration of j dot ds. This is written here. Similarly, for the fourth equation, which is divergence of electric flux density D is equals to QV, you apply volume integration on both sides. Volume integration of d dot d dot d tau is equals to volume integration of qv d tau, and then apply divergence theorem on the left hand side. You will get closed surface integration of d dot ds is equals to triple volume integration of qv d tau. This is written over here. Okay, so this is how the Maxwell's equation in integral form is written. Similarly, if you take the continuity equation, that can also be represented in the form of integral form. So continuity equation says del dot j is equals to negative del by del t of qv. So you apply volume integration on both sides. D tau is equals to minus d by dt triple volume integration of qv d tau. So you apply divergence theorem on the left side. You get closed surface integration of j dot ds is equals to minus d by dt triple volume integration of qv d tau. This is written as equation of continuity in the integral form. Okay, all right. Now let us see how to find the relationship between the circuit quantity and field quantity. So this, we all know that V is the volts, I is electric current, Q is electric charge, psi is magnetic flux, psi superscript E is electric flux, and U is magnetomotive force. So all these are circuit quantities, and these relationships tells you, these equations tells you the relationship between the circuit quantity V and the field quantities E, or the circuit quantity I and the field quantity J. So these equations are helpful in order to mix the circuit quantities and field quantities in Maxwell's equation. Okay, so now we are going to see how we can do that. So let's take the Maxwell's equation. So this is Maxwell's equation in mixed form. We will see how these equations came out by using Maxwell's equation in integral form and combining them with the circuit quantities. Okay, so let me write down the Maxwell's equation, the first Maxwell's equation in integral form, which is minus d by dt surface integration of b dot ds. Okay, this is Maxwell's equation in integral form, which we just now have derived. Now I am going to use this particular formula, that is psi is equals to surface integration of b dot ds. Psi is equals to surface integration of b dot ds. So if you see, this can be replaced with psi. So therefore this equation becomes closed surface integration of E dot dl is equals to minus d psi by dt, which is what written in this particular equation. Okay, so this is Maxwell's equation in mixed form, where this particular quantity is field quantity and this is a circuit quantity. Now let's take the second Maxwell's equation. In integral form, we know that closed surface integration of d dot ds is triple volume integration of qv d tau, is triple volume integration of qv d tau. Alright, and now if you see this particular equation, that is q total charge, q is total charge, is triple volume integration of the electric charge density q. Okay, so q is triple volume integration of the electric charge density q d tau. So if you see, this entire term can be replaced with q, so it becomes closed surface integration of d dot ds is equals to q, which is written in this equation. Similarly, for the other equations such as closed surface integration of h dot dl is equals to d by dt, surface integration of d dot ds plus surface integration of j dot ds. Now I am going to use this particular equation and this particular equation. Okay, so I is equals to surface integration of j dot ds and psi e is equals to surface integration of d dot ds. So this term and this term can be replaced with this and this. So the equation becomes closed surface and closed line integration of h dot dl is equals to d by dt of psi e plus I. This is the equation which is written over here, and this is also you can find it out where the right hand side is 0, so nothing will change. Alright, so the Maxwell's equation in a mixed form can be written like this. Similarly, the equation of continuity can also be written in integral form. We know that surface integration of closed surface integration of j dot ds is equals to minus d by dt of triple volume integration of qv d tau, and we already know that the total charge q is volume integration of the charge density qv d tau. So if you replace this with this, you get closed surface integration of j dot ds is equals to minus d q by dt, which is written over here. Okay, all right. Now let's move on to the Maxwell's equation in circuit form only. This is purely in circuit form. So if you see the Maxwell's equation in mixed form, we have seen that this closed line integration of E dot dl is equals to minus the time derivative of psi. So we have seen that closed line integration of E dot dl is equals to minus the time derivative of psi. So this closed line integration of electric field can be replaced with the summation of the voltage V. Okay, so that is how the Maxwell's equation in circuit form is formed, where all these quantities V, psi, U, I, everything is in circuit form only. Alright, that's why the first equation can be written as summation of V that is voltage, is equals to minus d by dt of psi. Similarly, line integration of h dot dl is equals to d by dt of psi e plus I. We know that the line integration of h dot dl is h dot dl is u from the circuit quantities, is u, but here this is closed line integral. That is why we have to replace it with summation of u is equals to d by dt of psi e plus I. Here also we have used summation of voltage v. Why? Because v is equals to line integration of E dot dl, but here we have a closed line integration of E dot dl, so that is why the summation of v is equals to the closed line integration of E dot dl has been used to replace the closed integration. Similarly, if you see the continuity equation here, we know that the closed surface integration of j dot ds is equals to minus dq by dt. Since current I is surface integration of j dot ds, so summation of I will be the closed surface integration of j dot ds. So this entire thing can be replaced with summation of I is equals to minus dq by dt, which is written over here. So this is how the Maxwell's equation in circuit form can be written. Okay, one more thing, that this particular equation, this is also known as Kirchhoff's voltage law, and this particular equation is also known as Kirchhoff's current law, KCL. That is also why it is known as conservation of charge, and this particular equation is also known as conservation of energy. Now, complex field quantities. Since we were using instantaneous field quantities E, H, J, D and B, now we want to represent Maxwell's equation in complex field quantities or in phasor form. So in order to do that, we must also know that how instantaneous field quantities and complex field quantities are related. So this scripted V is instantaneous voltage and this capital V is complex voltage, which is also written as VRMS angle phi. We all know that RMS value is written as Vmax over root 2, and this phi term can be written as exponential j phi. Since we know that V is equals to Vm cos omega t plus phi, so let's try to validate that if we substitute this V here, can we get this equation? So let's try it out. So V is under root 2 real part of the complex quantity V, which is Vm by root 2 e to the power j phi, Vm by root 2 e to the power j phi multiplied by e to the power j omega t, e to the power j omega t. So root 2 came out, real part remains, Vm e to the power j omega t plus phi. You expand this exponential, we get cos omega t plus phi plus j times sin omega t plus phi. You take only the real part, so you get Vm cos omega t plus phi, which means this and this are equal, which suggests us that any complex quantity such as electric field E can also be written as root 2 real part of E to the power j omega t, where this E is a complex field quantity which carries both RMS value E RMS and e to the power j phi, or in other words E max by root 2 e to the power j phi. Okay. Now we also know that the time derivative d by dt in phasor form can be replaced with j omega. So that is how these Maxwell's equations are written in phasor form. So we know that del cross E is equals to negative time derivative of B, where this E can be replaced with root 2 real part e to the power j omega t, and this B can be replaced with root 2 real part B into e to the power j omega t. So what we get is del cross root 2 real part of e to the power j omega t is equals to negative del by del t of root 2 real part B e to the power j omega t. So it can be simplified into root 2 real part of del cross e to the power j omega t is equals to root 2 real part of j omega B e to the power j omega t, which can be simplified as del cross E is equals to minus j omega B. Okay, or we already know that just by replacing the time derivative with j omega we can get the Maxwell's equation in phasor form. Okay, all right. So what are the key takeaways from this entire lecture? The key takeaways are, first, that the field quantities can be represented in terms of instantaneous field quantities, and complex field quantities or phasor field quantities, phasor form. Second, that the Maxwell's equation can be represented in terms of differential form, it can be represented in terms of integral form, it can also be written in terms of mixed form, that is using both circuit quantities and field quantities, and fourth, entirely circuit form. So the Maxwell's equation can be represented in all these 4 forms, actually 5 forms, where the Maxwell's equation is represented in written in terms of phasor form. Okay, all right. So at the end I have framed 2 questions for you, which I would like to see your answers in the comments. So the first question is, which of the following equation represents Maxwell's Faraday law. So you have 4 options, A, B, C and D. What I need to do is, you look at all these equations and try to think in your mind whether these equations represent the Maxwell's equation in differential form or integral form or mixed form or entirely in circuit form. Then you come to the conclusion that which Maxwell's equation represents Faraday law. Okay, so please write down in the comment section that what is the correct answer for question number 1. I have one more question for you. Consider the following equations shown below. So you have 4 equations, equation 1, equation 2, equation 3 and equation 4. Which of the following equation represent Ampere's law? So out of these 4 equations, you have to tell that which equation represents Ampere's law. So here also your approach should be to see and identify that these Maxwell's equations are written in which form. Then you finally comprehend that which equation represents Ampere's law. And please write down your answer in the comment section. So these are all the options, A, B, C, D, E and F. Alright, thank you very much. If you have any doubts, please write to me in the comments. Thank you.